Okay, good afternoon, everyone. Welcome again. Welcome to the first Tuesday seminar at the Warsaw University Astronomical Observatory, first this year, I mean. And today we have an honor to guest Jakub Klencki, who's an ESO fellow, but he's our own. We trained him here in this very building. He did his bachelor degree here and then master's degree in connection with TAMP, and then went for his PhD to Nijmegen, and now is an ESO fellow and is going to tell us about massive stars. Jakub, please.
Okay, thank you so much for the introduction. Thank you for being here. It's a real pleasure. I will indeed talk about massive stars, and particular massive stars that live in closed binary systems in which those two stars interact with one another, leading to very fun things, and a connection between massive stars and massive binaries and the gravitational wave sources. But first, for a bit of background, let's see if it works. Yeah, okay. So, massive stars find a connection to various areas of astrophysics all throughout the cosmic history. They're very hot and luminous, providing most of the radiation that reionized the universe back in the day. They are also characterized by strong winds and outflows with which they see turbulence in the interstellar medium. They enrich that medium with products of nuclear burning. And at the end of their lives, they become stellar black holes and neutron stars. And from the other angle, they also have a more passive role, so something we can observe even to high redshifts. They are so bright that they dominate the light from star-forming galaxies and young stellar populations, which allows, particularly in the UV, which allows us to study the cosmic star formation history of the universe. Massive stars also lead to some of the most energetic phenomena, gamma ray bursts, supernovae, and stuff like this. And most recently, the gravitational wave sources. And okay, I think that the two biggest challenges in the field of massive stars these days is first understanding the effects of binarity. We know now that most of the massive stars are not single. They are formed in binaries, triple or higher order systems, and most of those massive stars will at some point interact with their companion. And that mass transfer interaction and binary system drastically changes basic properties of a star as well as its final fate. There's many effects connected to binary evolution that we still don't understand, that are connected to this broader picture that massive stars play in the universe. And the other major challenge is understanding the origin of gravitational wave sources. So emerging pairs of stellar black holes and neutron stars that we can now detect with LIGO deep interferometers. So let's shift to the GW sources so far to start. And so this diagram shows the state of detections by the LIGO Virgo after 3 observing runs. The x-axis has no mean, but the y-axis shows the mass, and these are all the detections. In blue are black holes. Most of these are binary black hole mergers, but there is a few events with at least one neutron star component. We can also add neutron stars and black holes that we know from electromagnetic observations. So these are the black holes here. This is not complete because these are only black holes from X-ray binaries, mostly in the Milky Way, mostly low-mass black hole low-mass X-ray binaries. But also a few X-ray binaries in the nearby galaxies. I think something changed. Okay, I hope it's all good. Okay, and one thing that was noticed early on, once this plot was made, is that many of the black holes detected in gravitational waves appear to be significantly more massive than the black holes we know from X-ray binaries. We have plenty of black holes with 30 and above solar masses, whereas the black holes in X-ray binaries are typically between 5, 10, and maybe up to 20 solar masses. And so this led to the suggestion that maybe with gravitational waves, we are probing a population, or a significant part of this population comes from different environments than what we are used to observing with X-ray binaries. And specifically, that environment could be low metallicity, characteristic of a far universe or a distant universe, young universe, where metal-poor massive stars are characterized by weaker stellar winds, which helps in production of more massive black holes. That's the idea. And I'll come back to this a bit later. But as I said, this is a state of detections after 3 observing runs. In fact, most of these events come from the latest run. And this is because with every upgrade, there is an increase in sensitivity. So the detectors are probing a bigger volume of the universe. And so the prediction is that in the coming years, this number of detections on the gravitational wave catalog will go up orders of magnitude. We are here at the size of the catalog of about 100. And we may go to thousands or tens of thousands even before the third generation of detectors. So there is a chance, there is a hope that we'll really go into this data-driven side of gravitational wave astronomy, where we have plenty of detections to play with. And having so many events comes with some perks. When we have a lot of objects, we can start to maybe see some features in the distribution. And so I'm showing here as an example a plot of chirp masses of those events. A chirp mass is a combination of masses of both components. And the plot comes from the latest so-called population paper by the LIGO collaboration. And in the upper panel, you can see the chirp masses of individual events as well as the combined chirp mass of all of these, the posteriors. And in the bottom panel, you can see an attempt to recover the underlying population, what the distribution of the chirp masses of all the merging sources looks like, sources that are being produced. And okay, this is quite uncertain and really depends on how you do this at this point. We don't have that many detections, but you can see some features in a distribution like this. It's not just the power law. Maybe there are some local maxima, minima, and so on. And when you see something like this, it's very tempting to try to attribute those features to maybe different formation channels or sub-channels for the formation of these sources. And this sort of comes naturally because we have just so many different formation channels that have been proposed and discussed in the literature for the formation of gravitational wave sources. And this is not complete, but you can divide them into different types of channels. There are ideas which are based on the isolated evolution of binaries or triples. So basically, you have, let's say, two stars that evolve in isolation from the rest of the universe. Then you have channels where the task of bringing two black holes or two neutron stars close together is really onto the dynamical interactions between objects. So this happens in dense environments such as globular clusters or nuclear clusters, where those dynamical interactions are common and cannot be neglected. And there are other ideas, for instance, that these are primordial black holes after the Big Bang, which is very fun. But generally, we have many options. And to study, ideally, what we would like to do is to take a channel, or even all those channels, and make a synthetic population of gravitational wave sources, nothing to be compared to the data. And the way it's typically done, for even a single channel, we need a few components to do this. We need our cosmological model of the universe. We need some initial conditions, which means that we need to know how many stars have been forming all throughout the cosmic history at different redshifts in different galaxies of different types. What were their properties in terms of the composition? How many of these stars were in binaries? How many were in clusters? What were those clusters? I mean, there's a lot of input that goes into this. And we don't really know very well how early universe looked like, right? But then once we have those initial conditions, we have the formation channel itself. Let's say that's the evolution of a binary. So this takes of the order of 10 mega years. Very short, massive stars are short-lived. But then once you form the binary of two black holes or neutron stars, it may take a very long time for those two objects to slowly spiral in due to the emission of gravitational waves by the binary. And there is a delay time from the formation of this binary to the merger. And this delay time can take any amount of time, easily into a few billion years, or as long as the age of the universe. So even though with current detectors we're still probing basically the local universe, it might be that those sources that we are seeing were formed even by the first stars. And it's just been taking so long for the binary of two black holes to merge. And this is why we have to take this entire picture into account, which makes it extra complicated. And so I forget that I can use this. And so people have shown that just this component alone can lead to our lack of understanding how the early universe looked like, can lead to uncertainties, propagating to uncertainties on the predicted population of gravitational wave sources, easily by 2 orders of magnitude. And in part, this is because of the importance of low metallicity. I already mentioned that we have a preference for forming massive black holes from metal-poor stars. And this preference can take the form of a diagram like this, where on the y-axis, which what we call a formation efficiency of gravitational wave sources. So how much mass you need to form in stars to form one gravitational wave source, let's say, or an equivalent to this. And on the x-axis is the metallicity. And the black line, which is for binary black holes, shows what people typically find in population models from some classical channel. And this channel gives you a prediction that you really need to go to low metallicity, around 10% of the solar metallicity and below, to form those systems effectively. And when you compare that to how well we know the star formation history at those low metallicities, that is something that is not just easy to constrain, because most of that star formation happens in low luminosity dwarf galaxies that are difficult to detect. And so this example shows that the gray lines are constraints coming from star-forming galaxies at different redshifts or at different look-back times. And it shows you at the y-axis how many stars have been forming per unit of time, per unit of volume, at metallicities that are below 20%. And there is a huge uncertainty spread, more than the order of magnitude. And those lines and colors here show different assumptions that people modeling gravitational wave source populations have been using. And so those assumptions can be all over the place almost. And so this is one of the components that makes the task of modeling the population of LIGO sources challenging. And that's not the only one. And in general, we are sort of at a crossroad where, in order to model the LIGO Virgo sources, there are so many parameters that we have to put in, so many components of the model, that it's really difficult to come up with a way to make a prediction that could be compared to the observations and actually teach us something. And I think we have a bit of a long way still to go in order to help solve some of these issues and be ready to take the best use of the coming data of thousands of detections, because it's not obvious that if we have 100 times more detections, we will actually be able to solve these issues. And so there's a lot of being done to develop a different part of this picture, but something that I think is important and is the most closely connected to stellar evolution is to develop a better understanding of the formation channel itself. What are the key uncertainties in the stellar physics that are affecting our understanding of how we get the LIGO Virgo sources? How can we nail them down with maybe other observations as well? And so I will shift the gears now a little bit and talk about the formation channel of LIGO Virgo sources. I will put this as a sort of starting point. And this diagram shows one idea of how you perhaps, starting from two massive stars, and at the end get two black holes that are going to merge. And those diagrams, since we plot them sometimes, represent the evolutionary channels or formation channels in binary evolution. And I'm not going to go through all the details of what's happening, but basically you have two stars in a closed binary. They are changing due to their evolution. Maybe a star is getting bigger if it's in the binary that leads to mass transfer. At some point, one of the stars finishes its evolution, collapses to form a black hole. Maybe then the companion expands, initiates another phase of mass transfer. This phase here, common envelope. I'll talk more about this. For a long time has been viewed as the key stage of this formation channel. But at the end of the day, what you want to get is two black holes that are very close to one another, because they need to be close so that the gravitational wave emission can eventually merge that system within the age of the universe. And so the long time way of studying those channels has been the rapid population modeling of those sources with the codes such as Star Trek or BSC or COMPASS. And the approach to this is to make a bunch of approximations, to use pre-computed tables of how stars evolve, to use a bunch of simplified models for phases of evolution that we cannot model really in detail anyway, such as the common envelope or the formation of a black hole neutron star, where we cannot model on a large scale. It's a longer discussion. But this upside of making approximations is that you can really make millions or tens of millions of models and create a population, really populate your universe and make some predictions and stuff like this. And a lot of work is being done in that direction. But what I think is complementary and also needed is to take a more in-depth, slow look at particular phases of formation channels, try to understand the bottlenecks, what is really happening, and whether we have some observational counterparts of those stages of a channel. And so what we did here is try to focus on the common envelope evolution, the phase itself. And so let's talk about the common envelope for the little bit. The idea of this phase is that when you have a binary that already contains, let's say that's already a black hole, yeah, and the second star is still alive. At some point, that star becomes a giant and expands during its evolution. And so it initiates a mass transfer into the black hole. But if this giant continues to grow relative to this orbit very quickly, then at some point it will basically become as big as the orbit itself. So it will engulf the binary, such that the black hole is essentially moving inside the envelope of that giant star. If it's moving inside the envelope, it's feeling the drag of that gas in there. And so it begins to spiral inside the envelope, generating energy. That energy is put into the envelope. And when you put energy into the envelope of a giant star, it usually expands in response to that. And so if you put enough energy into the envelope, this envelope will basically expand to infinity. Yeah? The density drops, so the drag drops down as well. If you expand the envelope, the spiral slows down and also diminishes. So that if you do eject the envelope, then you finish with a binary here in the center, which is comprised of the black hole and the core of the giant star. And the envelope is maybe gone. So there's a lot of mass ejected from the system. But the condition for this to be possible is that the energy input from the spiral has to be greater than the energy needed to unbind the envelope, to eject it, times some parameter, because probably the energy transport is not fully efficient. There is some energy loss from the surface, from that system, for instance, in the form of an optical transient. And okay, so this is how it's often done to emulate the common envelope evolution. But let's maybe go back to this stuff. The alpha is efficiency, so it should in principle not be greater than 1. But if you take some system that you think you evolved with common envelope, you can estimate those two things, and maybe you come up with an alpha greater than 1, which seems at the face value is an issue. But this could mean that there is some energy source that we had not taken into account that operated in the past history of that system, or that the binding energy of the envelope of the progenitor giant, you overestimated that in your calculation, right? And so what we did is try to be quite careful with the binding energy of massive giant stars. Instead of using some approximations, we computed quantistellar models of massive giants at different metallicity, different masses. And then for the energy input, we considered all the energy sources that have been discussed in the literature with full efficiency and no energy loss as well. And at that point, we felt confident that if you put alpha equal 1 here, that means that you're being very optimistic, because probably you are not able to transfer so much energy into the envelope. And I think I will skip this. I will jump in here straight to the result. And the result is shown here in an HR diagram. So this is the computation we've done for massive giants of different, as I mentioned, different masses and metallicities, and then asking the question, at what point, if you put the black hole inside the envelope of that giant and do the common envelope phase, at what type of a giant star the envelope is so loosely bound that it can be ejected as a result of that in spiral, right? Where are those giants? And so this is an HR diagram, mass and luminosity, showing, there is a bunch of stellar tracks for reference here. And the green area shows where the common envelope ejection is possible. So these are the giant stars with loosely bound envelopes. That's all at the Hayashi limit here on the right. So these are convective stars. For massive stars, that would also be red supergiants. And those red supergiants are the largest of massive stars. They are basically a small core where a lot of the mass is, and the envelope is very diluted, very convective. There are a lot of stuff happening in the envelope, and it's very bound gravitationally in the first place. And so it comes as no surprise that these are the stars that you can envision the ejection of the envelope in the easiest. What we find is that basically only the red supergiants for which the common envelope is energetically possible. And so this comes with a bit of an issue. I mean, the red points here are the red supergiants that we know from the Small Magellanic Cloud. And there is an empirical upper luminosity limit, about 5.6, above which we don't observe any red supergiants. And this coincides with the Humphrey-Davidson limit. And this luminosity limit is true not only for the SMC, but also basically for all the galaxies in the local group where we can make a statistic. And so it seems that it's not metallicity dependent. It might just be, and this limit corresponds to initial masses of 40 solar masses on the main sequence. And so it might be that stars more massive than 40 solar masses never become red supergiants for various reasons that are discussed. One of the reasons could be wind, mass loss. They lose too much mass before getting there, possible. And this is an issue because we need those red supergiants in the common envelope channel to make black holes as massive as 30, 40 solar masses and so on. 40 we need stars more massive than 40, was the conclusion. And I want to advertise a recent paper by Emanuele Romagnola, who is a PhD student at the Copernicus Center here in Warsaw, where he really looked at detail at this and emphasizes, the need for us to understand the origin of that lack of red supergiants in the context of formation of gravitational wave sources from common envelope evolution. All right. Okay, so at the face value, it seems that there's an issue in the common envelope channel. Something that has been called as the classical channel before. Maybe it's not really able to form the most massive black holes observed in gravitational waves, about half of the population of them. And very briefly, there is a few ideas or habits to this that I think are being discussed and are worth mentioning, of how could the ejection of the envelope possibly be made easier. On one side is that the envelopes of stars that are interacting, that have accreted in the past, and those would be stars in X-ray binaries, so in the channel that is being discussed here, their structure is a bit different than normal stars. There has not been too many studies to actually show in what ways accretors could be different from single stars, so there are some preliminary results. But it might be that their structure is such that the envelopes are less bound, which would help in ejecting them. There's another idea, that another energy source that has not been considered here, and these are jets. If you have a black hole that spirals inside the envelope of a giant, creates a jet, then that jet, and actually just a supercritical disk with winds, could be a way of transporting super Eddington energy into kinetic energy, and those kinetic outflows are very easily coupled to the envelope, so they could provide so much energy, in fact, perhaps too much energy, in such a way that they would disrupt the envelope. And then there is a question whether there is even a spiral. But jets are definitely something to keep in mind that changes the energy budget discussion completely, possibly. Something that I think is quite interesting is the pre-common envelope mass transfer. So I showed you this picture, right? When you go from before the mass transfer to common envelope. But you don't go from A to B overnight. It takes some time. There is some phase of interaction before the mass transfer becomes unstable, before the dynamical spiral starts. And you can actually model this. We did that for one of the luminous red novae progenitors. So luminous red novae are those optical transients that we think are associated with common envelope events. That was for a massive yellow supergiant progenitor. So this was the yellow supergiant, basically. And then all the models, what happens, and honestly was predicted, I think in every case, would be that before the mass transfer becomes unstable, there is a phase lasting hundreds of years during which the mass transfer rate slowly goes up. And at that, during this couple of hundred years, a big fraction of the envelope can be transferred and probably ejected from the system. So by the time we get to the end spiral, the envelope is smaller, the envelope is different, it's less matter to unbind, so it's easier. But also there are some fun observational consequences for the appearance of that system before the merger. You lose a lot of mass from the system. That could lead to the brightening if some of the mass is being radiated. That could lead to the production of a lot of dust that you can see. It's an infrared excess from progenitors of luminous red novae. Okay, but this is something for another discussion maybe. I think another caveat here, and a lot of the research regarding common envelope seems to be heading in that direction, is a consideration that it's not really a one-stage process, or I already mentioned the first stage, but there's possibly also a stage afterwards. Maybe you don't need to eject the entire envelope to slow down the spiral. Maybe once you eject 90% of it, the drag slows down already. And what you're left with afterwards is, let's say, a black hole, and not just a helium core, but a helium core with some envelope on top. Yeah. So if you leave those layers on top of the helium core, then there's less mass that you need to unbind, and those are the layers that are the most gravitationally bound, so they're difficult to unbind to begin with. So that helps in the energy budget. There are sort of signs of this possibly found in hydrodynamic simulations of the common envelope spiral, although that's difficult because those layers are difficult to resolve in those simulations. So sometimes the result just comes from the way those simulations were set up to begin with. But I think some of those results could be visible. And that could be a big effect for convective donors, but maybe I'm not going to go into those details. What's interesting is if you leave some hydrogen on top of your helium core, also for lower mass stars, this configuration is not going to be stable for a long time. And so if you wait a thermal timescale or a couple of 100 years, that star that is partially stripped will re-expand again. And if it's in a closed binary, it will lead to another phase of interaction. That interaction could quite likely be stable, maybe even long-lasting, as some people argue. And observationally, if a companion is a black hole, that would look like an X-ray binary or ultra-luminous X-ray source even, with a blue giant or blue supergiant companion. Except that this donor is much less massive than the normal blue supergiant would be, because it already lost most of its envelope. So the mass transfer is much more stable than you'd normally expect. Those are results by Michel Vassink, a master student from Marek. Okay. All right, let's wrap this part up a little bit. I've been talking about the common envelope and trying to convince you that maybe it doesn't work as well as we had used to think in the information of binary black hole mergers, especially when you think about those massive ones, above 25, 30 solar masses. I still think that the common envelope channel is the dominant one for the formation of double neutron stars, and possibly also the low mass binary black hole mergers. There's a nice work by Federico Garcia on this point. I don't think I put it here, but yeah. But another growing alternative now is the suggestion that maybe you actually do not need the common envelope to happen during this binary evolution channel to form a merging black hole merging binary of two black holes. Sorry. The idea is that you start with a smaller system, so you don't need to shrink the orbit so much. And when you think about massive stars, it is possible to have a stable mass transfer evolution, even if the donor mass-losing star is a few times more massive than the companion. What happens if the donor is a few times more massive is during stable mass transfer evolution, the orbit shrinks. This just comes from angular momentum, binary orbital angular momentum conservation. And so if the progenitor stage here is a supergiant high mass X-ray binary, an ultra-luminous X-ray source, you can shrink the orbit sufficiently to produce a merging black hole binary at the end. Okay, so let's talk a little bit about stable mass transfer evolution in general. So usually it happens in the binary as a result of expansion. You have your star, it's doing something, it's burning something. When the fuel runs out in the core, usually the core contracts and the envelope begins to expand. The star becomes a giant. And this type of expansion is usually what leads to a Rorschach overflow in the binary system. So this plot here, this diagram shows the radius versus time evolution of a model of a 25 solar mass star with different colors showing different evolutionary stages. And so in blue, there is the main sequence for hydrogen burning phase. Then the fuel runs out, the envelope expands, the star becomes a giant, and there is a huge phase of expansion, very short phase. The star is out of thermal equilibrium. This lasts thousands of years, which we call the Hertzsprung gap. And during this phase, the star really becomes a red supergiant here, has 1,000 solar radii. Then it starts the core helium burning phase. And actually what happens here is you have the winds strip the envelope. So at the end of the day, the envelope strips and the star becomes a helium star. That's why the radius decreases. But we basically have two phases of expansion during the life of this star. The main sequence and just right after the main sequence. And so in a population of binaries, you can imagine that there's going to be two parameter spaces for mass transfer interaction. There will be, here as a function of mass and period, there will be closed orbit binaries in which the interaction happens already during the main sequence, so-called case A mass transfer. And there will be binaries in which the mass transfer is initiated as a result of this rapid expansion during the Hertzsprung gap phase, case B binaries. And now the textbook picture of the case B mass transfer initiated by this giant is that this is a rapid short-lived phase of thermal timescale mass transfer, with huge mass transfer rates, which over the course of a few thousand years maybe, strips the nearly entire envelope. Yeah, a few thousand years is nothing for the evolutionary timescales. So let's say if you start from a binary with a giant star and a main sequence companion, very quickly you're supposed to get to something like this, where you reveal the helium core and you maybe have a rapidly rotating companion. And those type of binaries are now being discovered more and more efficiently. And LP1 was the first famous one. And then if you have a compact object companion and you strip the envelope, then you produce in the massive star regime that would be a black hole and a Wolf-Rayet companion. And there is a few of such systems maybe existing. But okay, so this is, in a way, this is a very simple phase. Yeah? You take a star and very quickly you take away the envelope, and what remains is the helium core. And this is actually very useful because in order to understand a lot of the binary effects, what's being done is just to start from this point and target. To say, okay, we start, my star is in a binary, I'm going to model a helium star and see how that differs from just the evolution of a normal star that also has the envelope. I will say that I'm studying the binary evolution effects, which I think is a very practical choice. And this is being done to understand the binary evolution effects for the formation of a black hole neutron star, for the final spins of black holes from those formation channels. I'm not going to go into detail, but basically the taking away of the envelope is a sort of assumption, is an approach that is very useful and being used. But okay, there's an issue with this, and that is the effect of metallicity. So now the same radius versus time plot as before, but I added another line, also a 25 solar mass star, but at low metallicity of the small Magellan cloud. So in general, now the low metallicity star is smaller, it has smaller opacity, already during the main sequence. But what's important here is this rapid phase of expansion, the Hertzsprung-Gap phase, is much less pronounced in the low metallicity regime. Yeah, the star transitions to the core helium burning phase when it's still a blue supergiant. It has less than 100 solar radii. And then it does continue indeed to expand to a red supergiant phase, but on a much slower or longer nuclear timescale of core helium burning. And so when we go back to this plot, showing the parameter space for mass transfer, we now just get this area, lots of binaries in which the mass transfer will be initiated by the slowly expanding core helium burning star. And that's really something only possible for massive stars at low metallicity. And so what we're wondering about and what we wanted to find out is how does this impact the mass transfer interaction itself, whether it's indifferent compared to those Hertzsprung-Gap donors. So what we did was once again use the MESA, the stellar evolution codes, to compute binary models across all this parameter space for different metallicities. And I'm going to show you some of the results. So now this panel will show mass transfer evolution from a 25 solar mass donor. And there is 3 different columns for different metallicities: solar, LMC, and SMC compositions. And now, in all those cases, the mass transfer happens when the star has about 90 solar radii. So in the left panel, the solar metallicity donor will be during this rapid phase of expansion. The SMC donor, lowest metallicity, will already be core helium burning star. And the LMC one will be very close to the core helium burning phase at that point already, illustrated here. Not sure if it's visible though. But okay, so now let's see some of the results. For the solar case, well, we cannot see it very well, but we can zoom in. There is a bunch of lines which correspond to different mass ratios, but the mass ratio doesn't really matter. In all the cases, the mass transfer rate, which is in the upper panels, it reaches very high values. The lower panels show the envelope mass. In all those cases, almost the entire envelope is stripped very quickly, a couple of thousand years. Whatever is left is stripped later by the winds. So in all these models, you indeed produce just this helium star, a very hot and compact star on the thermal timescale. So that's the textbook picture I showed you before. But something different happens in low metallicity models. Yeah. In those cases, initially the mass transfer rates are very high, similarly, but they drop down, or the binary even detaches, some cases way before you strip the entire envelope. Yeah. So we can have a few solar masses even left on top of our helium core at the point where the mass transfer slows down. At that point, it may finish completely, depending on the parameters, or it may continue, but on a much longer nuclear timescale with lower mass transfer rates, all the way until the end of the core helium burning, which is where those simulations stop. And so that's quite a different picture than before, right? So now we have this mass transfer at low metallicity, which might be producing partially stripped stars, and it might be lasting of the order of 10 to 6 years rather than 10 to 4 years. And so this is going to have a bunch of consequences, not only for the gravitational wave sources. I mean, those partially stripped stars look a lot different. They are bigger than just helium stars. They are much cooler. And so they wouldn't be so bright in the UV, but they might instead hide among the OB star population. I will show a bit on that in a moment. And that also has some implications on the supernovae progenitors, where we think that a lot of the stripped supernovae are being formed by binary interactions, where we take away the envelope and you produce the stripped supernovae progenitor. But in the context of gravitational wave sources, I think the biggest implications of this is that in stars that you strip the envelope slowly, gradually, or not even fully, it will be much more easier to form a black hole rather than a neutron star. The recent results shows that in binaries, the limit between the black hole and a neutron star would go to higher masses, from 20 solar masses to maybe even 50. But this helps in low metallicity to not shift that limit too much. If we have this long interaction phase, then that can be observable in say ULX. And so if part of the population of LIGO Virgo black holes goes for a stable mass transfer like this, then the observational counterpart of the immediate progenitors would be ULXs. And there is some ideas of how to link the two populations as a function of redshift as well. Funnily enough, we do observe overabundance of ULXs in metal poor galaxies, but the issue is that a lot of those could be coming from neutron star accretors, I think. And what's also quite cool is that this longer lasting mass transfer and low metallicity effectively leads to tighter binaries at the end, because there's less wind after the mass transfer that would widen the orbit. And so it allows for the formation of binary black holes that will have the shortest delay times, and that will also possibly have non-zero spins in the secondary formed black hole. If after the mass transfer you have a black hole and Wolf-Rayet system, the system is close enough for tidal interactions to be strong, then those tides will spin up the Wolf-Rayet star. And if you assume that you preserve that angular momentum during core collapse, then you form a rapidly spinning black hole as the secondary black hole. And you have something that you can observe by LIGO Virgo. But okay, so these are some models. There's a lot of uncertainties on the stellar evolution side that are connected to all this, that are connected to how stars expand and how they interact. In particular, uncertainties due to mixing that happens in stars that we cannot model very well from first principles in stellar chaos. And so it's key to search for some observational counterparts to constrain those models. And I will skip this. I will just jump right into this diagram. So this shows the result from a grid of models at SMC metallicity, showing some predictions on binary interaction products created by, of stars that are already in the core helium burning phase. Now these are all models, both the dots and the grayscale. Okay, and what the colors show is. In red are the stars that have not interacted yet, or either because they will interact in the future or they are in very wide binaries. Those are post-main sequence stars. So we can see some yellow supergiants, red supergiants, and so on. And in green and blue are binary interaction products. So mass transfer really populates this diagram in all the many more places than just single stars. In blue are stars that are interacting already during the main sequence, so KTA mass transfer products. And green are the stars that interact as giants during post-main sequence evolution. And there are a few areas that I think are interesting and could potentially be constrained. So first of all, here on the left of the main sequence are helium stars, the hot stripped stars, some people call them. And so one prediction is that if indeed at low metallicity, for some masses, giants are not fully stripped, the giants are the green ones, then in this area here, you don't get stripped stars that are really green ones. You don't get them from wide mass transfer. So the prediction is that as a function of luminosity or above some luminosity, the number of stripped helium stars decreases. It should also decrease as a function of metallicity between Milky Way, Large Magellanic Cloud, Small Magellanic Cloud. This is not yet testable really because those stripped stars, in predictions that there should be many, but they are the easiest to detect in the UV. If they have a companion star, then optical surveys, the companion will be usually much brighter than the stripped star. So in order to find them, we need to go to UV and then confirm them spectroscopically. This is being done by Luca Goldberg and Maria Drau collaborators. And Van et al. Is the paper for the Milky Way. The results from the Magellanic Clouds are yet to come, and we'll see if they will be something interesting there. Other area I think is definitely constraining are the yellow supergiants. So I was talking about this long interaction phase from giants. And that would mean for yellow supergiants that some of them would live in binaries that even if not eclipsing, they would show some ellipsoidal variations because they are close to Rochelle filling or Rochelle filling. I think even 10% of yellow supergiants showing that type of optical variability would be surprising for the old models that should be enrolled quickly and would point towards those models of low metallicity, perhaps showing some real behavior. There's only one system that in Holmberg 9 galaxy that was found by chance. The question is if there is more. There is some work being done towards constraining the binary parameters of the yellow supergiant population, but I'm not sure if we will really find those type of objects yet. We'll see. And then finally, there are stars in the middle. The stars that I have referred to as partially stripped stars that lost most of the envelope, but not all of it. So instead of going here, they just overlap with the main sequence. But they're not normal stars. You lost most of the envelope. So on the surface, you see products of nuclear burning. They will be enriched in nitrogen specifically. And they will be undermassive for their luminosity. And one of such stars may already have been found in the SMC. This is a paper by Daniel Powell, who's a PhD student in Potsdam. And this binary here is the eclipsing binary in the upper HR diagram of the SMC. And it's pretty clear that the primary has 20 solar masses for the dynamical solution of the orbit. But its luminosity, if that was a normal main sequence star, points to 40 solar masses. So it's quite convincing, I think, that this star could be a mass transfer product that now is just much less massive because of mass transfer. And we've selected a bunch of other candidates in the SMC for which we're taking data now. Actually, it's already been taken, but it's being analyzed. And the question now is if this particular binary is just a single very weird star, or if indeed there is a population in the SMC of core helium burning giants that pretend to be main sequence stars, but are post-interaction. And there are some other classes of stars that cannot be explained by single stellar evolution models, such as slowly rotating nitrogen-rich stars, which at the face value agree with binary models very well, but there is some work being done to constrain whether they're binaries or not. So we need more epochs of data. But in general, I mean, I was showing you some results for the LMC and SMC. So the nearby metal poor star from dwarfs that are the most nearby, so they're the most studied. But there's more metal poor galaxies in the hood, a bit more far away, and with even lower metallicities. And so when we think about those metallicity effects for massive star evolution, I mentioned that they are important to pretty much all the models for gravitational wave progenitors. Most of those metallicity effects have not been confirmed or directly calibrated with observations. Even the winds have been poorly calibrated. And they are really at the core of some of the population models for the LIGO Virgo. So I think a lot of the work going into the future will be trying to see what we can really find in those dwarf galaxies, which of the metallicity effects predicted for the winds, for the binary mass transfer that I was showing to you, are happening in nature, and try to link those conventional astronomy, let's say, parts of stellar evolution to the gravitational wave boom of population modeling and to improve those models. This is basically my summary. I already said it, so I'll just leave you with the summary slide and take your questions. Thank you very much.
Thank you very much. Thank you, Jakub. Questions here from the room.
I wanted to ask about the rotation. How does it affect, like the initial rotation of stars in a binary, how does it affect the result that you propose? I guess there must be some synchronization at some point. Where and what happens to the rotation with this fundamental phase?
So if the stars are prone to fast rotation, then that star will lose its rotation due to winds at some point. That usually happens most likely once it becomes a giant, so after the main sequence. So let's say we talk about the interaction that happens after the main sequence, the initial rotation sorry, probably doesn't matter. Then, as you say, there is a chance for sorry. If the binary goes into interaction, tidal synchronization may become a case just before the mass transfer. So we expect that it will circularize the orbit if it was eccentric. It may spin up the star, but if it's in a wide binary interacting after the main sequence, that spin up is not significant. So it's not really going to matter, I think, too much. For the common envelope, it's more interesting whether you circularize the orbit or whether the spiral starts with some eccentricity. I think that's very interesting and not being really studied too much yet. Now, for the short period binaries that interact during main sequence, then the rotation can remain high if it was high initially, or can be induced by tides to be high. And that changes, first of all, that introduces all different types of evolution that I didn't mention here, like anti-homogeneous evolution that's predicted to happen in low-metallicity, could lead to LIGO Virgo sources, but it's never been observed yet, or not super convincingly. But it also makes comparisons like this a bit tricky. Rotation can induce mixing in stars. So it would also bring up nitrogen to the surface. And the rotational mixing is another way of making nitrogen-rich stars. So if you want to look for products of binary evolution, one of the signatures being nitrogen on the surface, then you need to find a way of distinguishing something that went for mass transfer, hence the nitrogen, or something that was fast rotating, hence the nitrogen. And so what we are going on for with Daniel is stars that are the earliest types. So they would be at the first phase of main sequence, that are enriched in nitrogen and slowly rotating. The idea is that for those stars, if they were initially fast rotators, they would still be fast rotators. They had not had enough time and enough expansion to lose them. But that's sort of the best we can do. Otherwise, some of the effects that we observe here are going to degenerate rotation and mass transfer interaction. That's the broad answer. So,
Okay.
Oh, no, that's a very good point. You would like to describe the presence of black holes of the mass 30 solar masses, and you present evolution of stars below 30 solar masses. So maybe there is some inconsistency.
I agree. I fully agree. So why I mostly show stars with lower masses? So I skipped the panel where the grids and the models that I compute actually go to. And the grid I show, I think 60, and then some of the newer results up to 100. But the issue is that the most direct comparisons are going to be for the lower mass stars, and those models are also easier to compute. Those models were computed probably 3 years ago, and at that point, I wasn't able, and I'm not sure if anyone else would be able to get models with all the physical components in them go up to 80 solar masses here, or 100. Now we have some numerical tricks that make it possible. And so it's just quite challenging, and we are sort of pushing the binary models like this with quantity-stellar evolution code and the mixing input here and the numerical resolution here is only now becoming possible. I mean, stellar evolution is an old field, and those type of codes were being developed 60 years ago. And the idea of mass transfer dominating the evolution of massive stars, I mentioned the Sana paper, and it's now being the revelation in the massive star field. But there is a paper by Paczynski from '67 where he actually writes that his prediction is that mass transfer interaction will dominate the evolution of eclipsing early type binaries, massive stars. That was 6 years ago, but then it was a bit forgotten. So at the end of the day, those are limitations and inconsistencies that we are working on. It's work in progress.
I was wondering, well, you mentioned a couple of times that we need observational evidence, and this research you're showing, it's kind of amazing, spanning through different observational areas. You talk about binary stars, right, which can be observed, and you talk about spectroscopic confirmation, then you talk about supernovae, which is all linked, right, and gravitational waves as well. But then I was wondering about one thing, because you mentioned X-ray binaries, they are part of this. Yeah. They appear somewhere. Yeah. But then the picture you showed with this black hole spinning inside the envelope, that should have a hell of an accretion signal. But it's not like a typical X-ray binary, right? But how long does it last? Is it like a couple of circles? Or is it longer? Is it detectable? That's what I'm asking.
So well, if there are jets, then it might be detectable because that accretion might cause And the idea is to look for asymmetries in the ejecta, for instance, in Outlander maybe. But the issue is you don't necessarily need jets to create those asymmetries. The spiral, I'm not going to be able to jump to the slides, but the spiral itself it takes too short to see.
Okay.
But I think if there is some phase of mass transfer after the common envelope, that could be lasting. So it's very interesting to try to understand what are the immediate products of that dynamical phase that we cannot see. One way to do this might be to go into the planetary nebulae, which we think are products of common envelope evolution, but in a lower mass regime. And then, depending on how much envelope you leave on top of the helium core, the temperature is going to be a lot different. If you see a lot of ionizing radiation from the center of the nebulae, that points towards the hot component, something that doesn't happen. But if there is no ionizing radiation, but this is in low mass regime. In high mass regime, it's very difficult. I will still advocate against common envelope channels in the really high mass regime of black holes. I'm not sure if there is a convincing even one system where we say it had to go through common envelope in that really massive regime. I mean, we have examples in low intermediate mass and neutron star regime as well. Black holes is
It's interesting that now we have way more binaries, well, which used to be binaries from gravitational waves than the actual interesting, binary systems, like the X-ray binaries, for example, right? The ratios change.
Well, there was this, somebody made this comment that if we are able with Gaia to see black holes in binaries by observing, for instance, the astrometric motion of the galaxy, the prediction from theory would be possibly you can see 100 of binaries with Gaia. So for a little bit, you could increase the number of black holes from electromagnetic observations about the GW ones.
Well, that's something which is
Nice.
which is to happen, I hope.
Yeah.
Any more questions here, please?
I have a question about the common envelope, which obviously you don't like very much. Why do you assume that the common envelope must be dispersed up to infinity? Why do you assume that it must, if the viral energy is significantly lower than the binding energy, then the envelope will stay around the binary, it will do its job, and then it may even fall back via the accretion disk on this binary.
Yeah, I know, I fully agree. So the idea here is that the envelope, I would only need to get rid of the mass in the proximity of the orbit so that the drag slows down. There is a certain binary mass, a lot of it still nearby. So first of all, for the energy consideration, that would mean that in my term 1/r, the r would not be infinity, but something smaller. So, but that lowers the amount of energy that I need to input to the envelope by maybe less than half, I would say still. And it doesn't quite solve the issue, because the issue here is of the order of a factor of 10. So those effects changing by a factor of 2 doesn't drastically change that completely. But what I think that more broadly, the understanding of what happens with this mass and the phases right after dynamical and spiral, I think it's something where we have to go to understand common envelope. I like common envelope actually. I just think it may not be dominant for the most massive ones. The lower mass regime, there is some nice work by the Andrei Pejas group, now in Czech. I forgot the name of the first author, but they are doing hydro simulations, where what they do is they input angular momentum into the envelope such that it expands, and they stop this not when it goes to infinity. I forgot the stopping condition, but essentially they follow post and spiral evolution with all this mass around, and they do 3D hydro so they can monitor the torques that mass will still exert in the system and change the orbital evolution, which I think is probably something that can happen in nature. But these are sort of first steps. Yeah. So I take your points.
I don't see questions here. Are there any on Zoom? There is someone asking a question on Zoom. Anthony, would you like to ask your question?
Yes. Hi, I'm calling from Montreal and the snowy country. And I really enjoyed this talk, a beautiful overview. But I do have one comment that is addressed to especially young people in science, and astronomy in particular, that you're speaking far too fast. For people like myself who are a bit older than the average, and perhaps non-experts, slow down so that we can absorb what you're saying. I think it boils down to reducing the number of things you talk about. But anyway, I have a specific question. You mentioned red supergiants up to 40 solar masses, but observationally, this is no longer a valid value of upper limit. Works by Phil Massey and collaborators have shown that there are no supergiants, no red supergiants above about 25 solar masses in our own galaxy and nearby galaxies in the local group. So this needs to be somehow folded into the theory that you talked about.
Yeah. Thank you for both of your points. I think both are valid. And I often talk too fast. Apologies for that. And greetings to Montreal. For the masses, there is work by also by Ben Davis on similar topics on trying to constrain the upper luminosity and of red supergiants. I always feel like, as someone who does the stellar evolution calculations, I always wonder how well you can assign the mass of a red supergiant, knowing its luminosity and its atmosphere. But that's maybe I'm not really an expert. I just suspect it's probably a bit uncertain. But of course, either way, 40, 20, 30, it's below the masses that we need to form, I think, 30 or above solar mass black holes. So the issue certainly stands, I think.
Okay, thanks. That's a good answer.
Right. I don't see any more questions, nor here, nor there. So let's thank our speaker again. Thank you all for joining. Thank you.